Adesso passo la parola alla professoressa Elena Selli, coordinatore del gruppo del comitato organizzatore di questo convegno, che introdurrà la conferenza del premio Nobel 2019 Stanley Whittingham. Prego Elena, ovviamente passiamo all'inglese adesso.
Okay, good afternoon to everybody, and I have the big honor of introducing Professor Stanley Whittingham, who is going to give the opening plenary lecture of this Congress, which is the 27th National Congress of the Italian Chemical Society. Professor Whittingham is very well known everywhere, and it is a big honor, and we are very happy that he accepted our invitation to open our Congress. Professor Whittingham was born in England, in Nottingham, and then he studied at Oxford, and then he went to Stanford as a postdoc. Presently, he is a professor at the New York State University, and his research are a milestone in the field of lithium-ion batteries. For this reason, he received the Nobel Prize, as Gaetano told just 1 minute ago, in 2019. So thank you, Professor Whittingham, for being here with us today, and we hope that you might be our guest in the future when this situation has changed and you might fly to Italy. Thank you.
Hello, everybody. Can you see my slides? Or okay. Oh, you see it better now?
Yes.
Okay, thank you. Thank you very much for the invitation. I would very much have liked to be with you in Italy, but the virus does not seem like it wants to go away. So what I would like to do is really lay out a little bit of history of the lithium battery as a kind of foundation as to what we can do in the future as chemists or as materials folks. And I show you 3 examples of lithium batteries to show the extremes we can think of. On the left-hand side, this is a grid storage facility in California, and I'll touch on that in a moment. It's by far the largest in the world. In the middle is a new BMW electric vehicle, which I think is on the market right now in Europe, but not yet in the US. And on the right-hand side is another grid storage facility. And this one was being commissioned, hadn't started up, and you can see one of the units caught fire. So this is one of the challenges, I think, for chemists. How do we make lithium batteries safer? Let me just thank the United States Department of Energy. They've supported my work for the last 30 years, and without them, I wouldn't be doing what I am doing. So let me just give you a roadmap. Really, lithium batteries started about 1972, 1973. And really the first large international conference that led up to lithium batteries was a NATO meeting in Belgrade, Italy in September of 1972. So really everything started in Italy, and with a bit of luck, maybe we can have a 50th anniversary meeting in Italy in 2022. I'll briefly talk about the potential impact of batteries on the cleaner environment, then get into some of the limitations and some opportunities and challenges for chemists. I'll then have a few messages for maybe our younger folks in the audience. So let's look at where we started out. It was Esso, which is now, I think, ExxonMobil around the world. They had the foresight in the early 1970s to become an energy company, and they were large in fuel cells, batteries they wanted to get into, and solar cells. And we did some work in 1972, which they thought was good. They were willing to invest in it, just like investing in an oil well. And they built up several $1 million, in those days dollars, to build up a manufacturing and engineering facility. And on the right-hand side, you can see two of the batteries that we built at that time. The top one is a paperweight we gave away to potential customers. Small coil, a watch, and a solar cell. This particular one is still in my office, and it's still working about 45 years later. So lithium batteries will last a long time. At the bottom here is a battery that we exhibited at the electric vehicle show in 1977. It's 6 inches by 4 inches by about 1 inch thick. By far the largest battery until maybe 10 years ago for a lithium battery. And it cycled a motorcycle headlamp on and off. So that's where we started. Here's where we are today. I'll show you a few examples on this side of vehicles. A small 2-seater car you can rent in Bermuda. And my wife and I had our 50th anniversary there in 2019 and rented this car. And it was new off the ship maybe 2 weeks prior to us renting it. And it is an Italian electric vehicle. Tourists are not allowed to drive in Bermuda until they got these electric vehicles. So this was a big plus. On the right-hand side is the other extreme, really, in electric vehicles. This is what we call a 16-wheeler, all-electric truck. And on the right is a garbage truck. And the garbage truck is really an ideal application for electric vehicles because it stop, start, raise, lower all day long. And I had the opportunity of driving both these at their test track in Washington State. Beneath that, I show you a latest Mercedes EV bus. This one is using solid-state batteries. So people are talking about making all solid-state batteries. This is probably the first commercial large vehicle with solid-state batteries in it. And the this battery option, I think, is available right now. What batteries do is enable renewable energy. And I'll show you a solar picture of the sun here, then a wind farm here with 16 megawatt hours of lithium storage to smooth the output from that wind farm. So wherever you have a large solar system or a large wind system, you're going to need storage of one sort or another. But let's look at what really has changed in the last 5 years. What is driving this field is that electricity is now lower cost from renewable energy than from fossil fuels. And to make that impact, if you look at Texas, and I chose Texas, it's what we call a red state, not climate friendly really. 94% of their future planned generation as of last year was renewable. Mostly solar, some wind, with quite a lot of storage to go with that. A little bit of gas, but essentially nothing else. In Texas, Tesla is also building a storage facility. This is 100 megawatts. This is opening this year. But this is tiny compared to the system in Moss Landing. That's about 1 hour south of San Francisco. This is 1.2 gigawatt hours. This is largest in the world by about a factor of 4. And this went fully operational last December. So this shows you the size of battery storage systems we can have now compared to what we were thinking about 30 or 40 years ago. This is an ideal location for a storage system. This was an old gas-fired power plant, so a dirty power plant. And they took out all the gas-fired system so that all the grid infrastructure is then just connected up. This is going to expand to 1.6 gigawatt hours this year, and they got the okay to expand to 6 gigawatt hours in the next 4 to 5 years. But let me get back to the batteries and show you what some of the issues we have. We talk about lithium-ion batteries because almost none of the rechargeable batteries today have lithium metal in them. That's because lithium metal will form dendrites when charged, and the dendrites then cause shorting of the cells, as I show you here. So a challenge for chemists is to come up with electrolyte solvents and systems so these dendrites cannot grow. These basically penetrate a separator in between. So that's one of the big challenges, the lithium batteries to go back to lithium, and I'll show you in a second why we want to do that. But let's just look a little bit at the history, where we started out, where we are now, and then a little bit about where we're going. So as I mentioned, we started out in 1972. We worked with a pure lithium anode. That forms or tends to form dendrites which are reactive and therefore can cause self-heating and eventually burning of the cell. Exxon switched to aluminum. It forms a 1-to-1 alloy. That is okay for maybe 50 to 100 cycles, but then it fails. So it was Akira Yoshino who developed a carbon-based anode, which also used intercalation reactions. So let me show you what I mean by that. This is a typical battery. You have an anode, a cathode, and in between an electrolyte, 3 key components. In a lithium-ion battery, all the reactions are intercalation reactions. If you want to look up what intercalation means, it used to be used for inserting or intercalating February 29th into the calendar year for leap years, then taking it back out again, totally reversible. I understand the Romans intercalated 3 extra months into the calendar year because someone miscalculated the number of months at one point. But in chemical terms, it just means we're going to insert, in this case, lithium ions into a structure without that structure changing, except for maybe a small expansion, no crystal structure change. Same on the anode and the same on the cathode. So Akira went to carbon. Today, we have to get the carbon out because you need 72 grams of carbon to store 7 grams of lithium. So the challenge for the chemist now is to come up with materials that can store more lithium and do it safely. A lot of work on tin and silicon. Both react with more than 4 lithium ions. But in the case of silicon, the surface is so reactive, the cell capacity fails. So the goal, as I say in the end, is to go back to lithium if we can, we get the full capacity. On the cathode side, at Exxon, we worked on titanium disulfide. This is a layered compound, so it's intercalating lithium between the sheets. This is about 2.5 volts. John Goodenough, who was then at Oxford, saw our work and he was working on the magnetic behavior of lithium cobalt oxide. And he said, the structures are the same. I'm going to try this in the battery. And this is what we still use today in applications which need a very high volumetric energy density, such as your computers, your phones, and your watches. But cobalt is much too expensive for large applications. So the cobalt has got switched out. You've now put nickel and manganese in there, or nickel and cobalt. And in many cases, you put nickel, manganese, and aluminum in there. So this lowers the cost. But still, cobalt is expensive, and there are child labor issues with cobalt. So it eventually has to go. John also came up with the phosphate structures. These are lower cost materials, but much lower energy density. And I'll show you some of these in a couple of slides. So these are of great interest, particularly in China and for low, small distance cars. We don't need higher energy density and lower cost cars. But the energy density, I say, is half that of the layered oxide. So we and others are now looking at how can you put 2 lithium ions or 2 sodium ions into a structure and get the energy density back up again. So let's look at what was special about titanium disulfide. a very simple layered structures I've shown you here. Titanium's octahedrally coordinated by the sulfur. Then we have an empty van der Waals layer gap in here, and we can intercalate lithium into this gap. The lithium ions go in here and the electrons go into the conduction band of the TiS2. It is, for all practical purposes, a metallic conductor. So it's very easy to get the electrons in and out as well as the lithium ions. And you'll see the slope here is just because we put the electrons in the conduction band, we're filling it so we get less and less energy out. But this is also very important, this slope, because from the voltage you can tell the state of charge your battery. So this one, I'll show you some data at the bottom here. Don't worry too much about it. This is run at room temperature, 10 milliamps per square centimeter. And I'll get back to that in a second. This conducting lattice can intercalate a whole range of atoms and molecules, you name it, it can go in there, provided it can donate electron density. So in the middle, I show you some data on the sodium analog, also room temperature. You can see now we get multiple phases, 3 different phases at least, plus the starting phase. So we've got 4-phase system here, single phase for lithium, no nucleation of a new phase, and the large voltage change. So very little interest now in sodium batteries using sulfide cathodes. This metallic behavior of TiS2 and its soft lattice means that multiple charged ions can also fairly easily diffuse in it. And Linda Naser at Waterloo University showed 3 years ago that you can get magnesium ions in and out of this lattice very reversibly, and you can see very little polarization here, the same voltage drop. She ran more than 40 cycles on this with essentially 100% Coulombic efficiency. So she showed the feasibility of building a magnesium battery, but you see the challenges of magnesium. She had to go to 60 degrees centigrade compared to the 21 for lithium, and she had to go to 0.04 milliamps per square centimeter. So low current, high temperature, but feasibility. And the other key point to note, the voltage of the magnesium cell is almost 1 volt lower than that of a lithium cell. So this means really magnesium batteries are not attractive. Sodium batteries might be. There are a few folks, particularly in Spain, looking at calcium batteries. Calcium batteries would have a higher voltage. But we need to understand magnesium, calcium, sodium, potassium, and lithium to better understand the lithium cells. So let's look at just what the opportunities are for us. Today, if you look at a lithium-ion battery, you get less than 30% of its theoretical volumetric capacity or energy density. That means there's plenty of opportunities for us to improve the chemistry and the electrochemistry. And if you look inside this oval here, you'll see that here the typical percentage is 11% for lithium iron phosphate, up to 25% for layered oxide. This one is 80% nickel and it has a silicon-based anode. So we should be able to increase these. This is on a volumetric basis. This column's on a gravimetric. So on a gravimetric basis, it's still only 25%. Our goal right now in the research area is to push this up to 50%, to double the gravimetric energy density. To make that work, we've got to take out most of the carbon because it takes up half the volume of the cell. We need to use all the lithium in the oxide or go to 2 lithiums in the phosphates. And for the physical chemist, we need really to have materials that have higher ionic and electronic conductivities. So TiS2 is a metallic conductor, but the layered oxides are poor semiconductors and the phosphates are essentially electronic insulators. If we can improve that conductivity, we can increase the thickness of the electrodes and therefore cut out some of the current collectors and separators. So let me show you some of the approaches being taken to increase the energy density. A key finding is the more nickel you have in your layered oxide, the higher the energy density. So I'll show you, which is now a famous plot from Dr. Sun's group in South Korea. The bottom axis here is the discharge capacity. So if you want to get above 200, you've got to go above 80% nickel. But if you get that high, then this material is thermally unstable. What do I mean by that? If you heat this material up to 220 degrees, it will lose oxygen. So all these layered oxides are metastable compounds. So as soon as you take the lithium out, you nickel 4+, and the metastable, they want to lose oxygen. So we have to stabilize them by some means. If you want the highest stability, this is essentially 100 degrees more stable than the high nickel. This is 1/3 nickel, but then this has a much lower discharge capacity. In the actual operating batteries, you never expect to get to this temperature, but the thermal stability is our direct measure of how reactive these materials are with our organic electrolyte solvents, and this relates to the capacity retention. So we're trying to get into this blue box, 100% capacity retention, great thermal stability, and high energy densities. So right now, most commercial cells are using what we call 60% nickel, and this is the nomenclature you'll see in literature. So it's 3-3-3, that means 1/3 nickel, 1/3 manganese, 1/3 cobalt. Right now, Tesla is using 90% nickel in their nickel, cobalt, aluminum, 5% cobalt, and 5% aluminum. So we have this challenge. If we want higher energy density, we're going to lower the safety barriers. Ideally, we'd like to take out the nickel and the cobalt and use just pure manganese, but manganese oxides tend to convert to a spinel structure, and they tend to be certainly to dissolve some of the manganese into the electrolyte. So there's a challenge there, but there's a lot of work going on to make manganese work. So let's look at where we stand right now. I said we have a program, and by we, I mean this is a Battery 500 consortium in the United States. It's been going for about 4.5 years now. And I just show you some of the data here. When we started out, after the first year, we could get charge and discharge this material about 50 times at 300 watt-hours per kilogram. Year later, we're above 200. The following year, we pushed the energy density up to 350 watt-hours per kilogram. And as of today, we've got about 400 cycles at 350 watt-hours per kilogram. So we're pushing the energy density up. But what we are doing to do that is we've taken the graphite out. We're using pure lithium metal with its associated challenges. So we're having to understand lithium plating. We've also changed out the carbonate-based electrolyte solvent and the salt in that solvent for ether-based electrolyte, because ethers plate lithium better. So it's a big challenge for every chemist to come up with new electrolytes. The electrolyte in the lithium-ion battery hasn't changed since 1990. So it's more than 30 years old. We surely can do better. This is what a typical particle in the cathode of a lithium-ion battery looks like. We call it a meatball. It's made up of small primary particles, maybe 200 nanometers across, and the secondary particles anywhere from 3 to 20 microns across. These pack very efficiently, whereas the small ones by themselves would not. This is a typical cell we use. We call them pouch cells. They're 2 ampere hours. And this work is mostly done by Jay Zhao at Pacific Northwest National Lab. She was a PhD student of mine. She makes the cells. They then shipped off to Idaho National Lab to be tested. So they're made in one place, tested in another place. So it's totally independent. So the challenge is, how much higher can we get the energy density? We really need to go higher than what we've got here. And the challenge in these materials is the volume of a host material, lead oxide in this case, you just put lithium in and out, can change. And this plot here shows you the volume change as you take the lithium out of this material. So you can see if we have a normalized volume of 1, if you take all the lithium out, or close to 90% of it, you're losing 8% of the volumes that material is contracting. And in this meatball configuration, where these primary particles are all next to each other, that expansion and contracting causes the material to crack. That is what causes capillary fade. You now get new solvent in there, reacts with the surface. And as Jeff Dance pointed out, it doesn't really matter how you modify this material. With pure nickel oxide, you have a 2-phase system. If you do anything else to it, then you go to single phase, but the volume change is still the same. So he is saying this is potentially a limit with this meatball systems, and this is at 210. Dr. Sun in South Korea has come up with exactly the same conclusions independently. So it's got capacity retention here. If you push it above 210, you can see the capacity falls off very fast. So this means we've got to use all the capacity that we have above this voltage. Okay, so we don't stress the electrolyte too much. And what happens, we found out in all these cells, we've got to use all the lithium. And the big challenge is, if you charge this material up, here's the voltage on this axis, the capacity here. You charge it up typically up to about 4.3 volts, 4.4 volts. Then you discharge it. You lose capacity on the very first cycle and you do not get it back. That capacity we have to recover. That's at about 3.5 volts, very stable regime in the electrolyte, so it's not going to damage the electrolyte. We can get more capacity by pushing this to higher and higher. So I say that volume changes and the material becomes more reactive. So our challenge was to find out what causes this and how can we get rid of it. So what we found out pretty soon is if we measure the diffusion coefficient, as I show you here, the black is the indiffusion, very stable until we get to about 70-75% lithium in, then it falls off the cliff by about 4 orders of magnitude. So clearly the diffusion mechanism here is really hurt if you go to high lithium contents. And you can think of this as if we had been in Milan, the lecture hall was full, say to 80% capacity. Any new attendee coming in would have to find a seat. The empty seats would invariably be in the middle of the rows. So everybody would have to move to allow that person in. Turns out the diffusion mechanism in these materials is you need 2 vacancies for the lithium ion to easily move. So you need 2 seats to be vacant. So this is why it falls off very fast. Fast charging is not an issue. You can see the open circles here. They show you the diffusion coefficient fast charging. Only the very last 10% does it start falling off. And again, you can think of the analogy of a lecture hall. When the class is over and the students leave, they can all just flow out very easily. So we decided to see if diffusion was really the controlling mechanism. And what we did here was to cycle cells at 2 different temperatures and at different voltages. And I'll show you in this plot here the same cycling curve, but at 4 different charging voltages, 4.2 up to 4.8. We would charge up to this voltage, then discharge. Then we'd hold the cell at 2.8 volts. So the lithium ions could keep diffusing in. And you can see we get quite a lot of it back. Same at 4.4. 4.6 is a bit better. But you see by 4.8 volts, we're getting this separation of the charge and discharge, and it's not going as far back. What's happening here is at 4.8 volts, the oxide is too reactive for the electrolyte, so it's actually forming a resistive layer on the surface. So that's room temperature. Go to 45 degrees centigrade. You can now see I've just shown you 3 of these. 4.4 volts, we've cut this gap down a lot down to here. 4.6 volts, it's not quite as good, and 4.8 volts is even worse. But you now see these curves are opening up at 4.6, opened up much more at 4.8, and the reactivity is getting much worse. So clearly we can't use these carbonate solvents at high voltages, but also clearly increasing the temperature. Lithium to use in-cell fusion is a controlling factor in these materials. And we have a few clues to help us solve it. First, lithium cobalt oxide, similar structure, but a multiphasic material, does not show a first cycle loss. And so we did a comparative test between 80% nickel and cobalt oxide. The black here is the room temperature cycling. The red is the 45 degrees cycling. And in this case, we held it at 2.8 volts for 100 hours. You can see we get all the lithium back in. Most of it's back in at 45 degrees. Anyway, in this case, we just cycle them up to 120 milliamp hours per gram. Cobalt oxide, you can see no first cycle loss, essentially no difference, room temperature of 45. So our feeling is we should be able to modify the layered oxides to make them behave more like lithium cobalt oxide. And one way to do that is to substitute species into the lattice and or coat them. So I show you here an example of just a coating reaction. And by coating, what we do, we immerse our meatballs into an alcoholic solution of a lithium niobium oxide compound, let it soak in, and then we fire that at, in this case, at I think 500 degrees centigrade, and then we get a surface coating as shown here, and it diffuses into the first few nanometers of the surface. So a little bit of substitution and the surface coating. What we have shown, in fact, this surface coating is a mixed lithium niobium manganese oxide, and some of the manganese has come out and the niobium's gone to take its position. But you can see just 1% of this solution by weight cuts down this first cycle loss by 50%. So we've got a clue this works. We now got to try to push it all the way in there. And right now we're working out at solutions that do not contain any lithium, because these meatballs tend to have lithium carbonate on the surface. So by using a niobium oxide reactant, we can in fact react that lithium carbonate and get rid of the carbon dioxide. So I showed you earlier, meatballs is what people use today. This is what we start out in 1976 with TiS2 single crystals. Sony, using lithium cobalt oxide, used very large single crystals, and this picture is one of Jeff Dahn's. I could find it more easily, where the particles are about 5 microns. Nishi at Sony, in fact, used 20 microns or larger. And so this should be microns at the bottom here, not millimeters. So they use single crystals. Jeff Dahn has now made single crystals of the 50% nickel, and Jay Zhao's made them, I think, with close to 80% nickel. See the difference in behavior. And it turns out there's essentially no cracking if you use single crystals. If you keep them, Jay says, at 3 microns or less, they don't crack. So we don't have the problems here. So single crystals also have less surface area, so less side reactions, which will give them much longer life. And they lead to what's now being called 1,000,000-mile batteries. So batteries that will cycle for 1,000,000 miles. We're never going to actually use that in vehicles, maybe taxis, but I think all the other components would fail first. But what it does allow, it allows electric vehicles to be permanently plugged into the grid when they're not actually driving. So they can be used to smooth the grid, act as storage in your home. If you have a power blackout, you can use the electricity from your car. And this will allow the utilities, the grid operators, to have a smoother grid and a lower cost grid. The challenge for chemists now is how do we make these in large quantities and without using too much energy? Right now, we'd go to high temperature to make these. So we need to make them at a lower temperature. But we now have a clue that if we go to larger crystals, this will lengthen the life. But I should warn you, this will reduce the power capability because you've got less surface area and therefore less diffusion surface. Let's look at some other opportunities as I cover the last few slides. I said we start out with TiS2. It turns out folks in British Columbia worked on molybdenum disulfide, molybdenite, naturally occurring ore. They used that for many years and commercialized it. John went to cobalt oxide. Then we had work on this lithium iron phosphate. And this is a tunnel structure, so much more stable than the layered structure. It does not evolve oxygen. Okay. But it is an electronic insulator, so it needs quite a bit of carbon, but it does not show a first cycle loss. And as I said, it has a much lower energy density. There's some work going on now on 4-volt lithium manganese phosphate. This will raise the voltage from 3.5 to 4, which will help a little bit. But our goal is to actually look at 2 electron systems, and we've chosen vanadium phosphate for that because phosphates are stable. The vanadium go from vanadium 5 to 4 to 3 plus. So we just have to show, is that feasible? This is something the field's been looking at for several years. Obviously, putting 2 lithium ions in reduced the amount of transition metal, cuts the cost. It increased the energy density by maybe 50 to 70%, not double, because the voltage is low on that second redox couple. This is just 3 examples of prior work. We worked on vanadium diselenide in the 1970s and cycled 2 lithiums in and out with no problem at all, but it's at too low a voltage to be of interest. Mike Thackeray looked at layered oxides. Again, you can put 2 lithiums in there, but the second lithium's at even lower voltage, so 0 interest in that case. But in about 2005, we showed that this vanadium phosphate could take in 2 lithiums, one about 4 volts, one about 2.5 volts. We stopped work after about a year on that because of concerns about vanadium that time, but those concerns have gone away now. You could use as the anode lithium, sodium. In principle, you use magnesium, calcium, or zinc. We have tried magnesium with our compound here. Magnesium is what we call a selfish cation. It goes and takes one of the oxygens and makes magnesium oxide. It will not readily intercalate. So we set out to make this compound. It turned out it wasn't easy to make it in an electrochemically active form. But in the end, we made it by a solvothermal, hydrothermal approach. This is an approach we favor, and we'd like to make the layered oxides by the same approach. You just dissolve all the reactants, heat them up to about 180, 200 degrees centigrade for 3 days. This temperature is the waste heat temperature of a chemical refinery. So it costs you nothing. So this is a big plus. We, in fact, don't need 3 days. You can cut this down. Doing that, we formed crystals of the hydrogen intercalating material. And if you heat treat this, you can get the empty vanadium phosphate out of the structure. And you can see this is now a 3-dimensional structure, so lithium ions can go in all 3 dimensions. An important thing that chemists can help us, all of us do, we can't do all our understanding using battery cells. Battery cells have binders in them. They have carbon black and other materials, current collectors, so they're a bit messy. So back at Exxon, we developed several chemical reagents that could mimic electrochemistry. And probably one of the more important ones is butyl lithium. This can intercalate lithium just like as an electrochemical cell. It is a bit overreactive, so it's about 1 volt versus lithium, so it may over-reduce. But the great advantage is the side products are butane, butene, or octane, easily gotten rid of. So you've got nice materials you can do X-rays on, you can do physical measurements on, and thoroughly understand the material without all the other bits and pieces on the electrochemical cell. And what we found out to our great glee was when we put 2 lithiums in this material, only by 8.5%. This saying the material shouldn't be stressed too much. This is less than graphite expands when lithium goes into it. So I show you here the crystals were made of this material, little cuboids. They're about 100 to 200 nanometers in size. We then mix them with a bit of graphene rather than carbon black. Graphene has a much larger aspect ratio, so can coat the materials better. When we do that, then this is the cycling behavior we get. Vanadium 5 to vanadium 4 and this 4 volt plateau, then vanadium 4 to vanadium 3 on this sloping lower redox couple. And you can see from this, the black curves is the first cycle, the purple one is the 50th. So this material is, if anything, behaving better on the 50th cycle than it's behaving on the first cycle. So we've got proof of principle that we can intercalate 2 lithiums into a structure without damaging that structure. There are still several challenges with this material related to, particularly related to the reaction here. And I think the next slide will show you what I mean by that. So we have 2 voltage regions, our high voltage region. In here we have a 2-phase reaction. So we have VOPO4 in equilibrium with LiVPO4. So we have to nucleate this phase. And this is why we get a flat plateau here. This shows you the rate of reaction. So I should explain, I think C rate means you discharge a charge in 1 hour. 0 of 50 means you take it 5 hours. So you can see if we take this for lowest rate, we get almost the theoretical capacity of 150, but the capacity falls off very fast as we increase the power. This is just shown again in this plot. 0 of 50, almost at the 150. If we then, having gone to C rate, take it back, we get back to where we start out. So this is not damaging the material in any way. In direct contrast, the low voltage regime, so if we get this material, discharge it all the way down to 2 lithiums, so now we're at theoretical capacity of 300, then just cycle up to 3 volts in this range here. You can see these plots are now totally on top of each other, whether it's CO 50 or C rate. The difference here is just the resistance loss in the electrolyte. So in this single phase region here, the material reacts very fast. So our challenge is now, how do we modify the high voltage region to make this react faster? And the other challenge we have in here, you can see now the Coulombic efficiency is poor in this low voltage region, even though it's fast rate. We put in far more capacity than we take out, but note, we take out the theoretical capacity. So what we have going on here is some reaction with the solvent. We're reacting the solvent and basically VOPO4 is acting as an oxidation catalyst, which should be no surprise that it's used in the chemical industry to do that. So we need better electrolytes, better salts. Here again, we need the chemist to come up with those. But we've shown the feasibility of these 2 lithium systems. I expect there are many more like it. So we need to hunt for new materials and better electrolyte systems. So a few comments and my conclusion on what's next, because really what we're all interested in is greener and safer energy. These lead oxides are going to keep dominating. We've got to get rid of, I think, of all the cobalt, and I think this is going to happen. The phosphates are going to have key markets, particularly I think China favors lithium iron phosphate. Tesla is making their Model 3 cars in China with lithium iron phosphate batteries and then shipping those to Germany, and so the Tesla cars in Germany are using lithium iron phosphate. There's really no reason why these lower cost, safer materials aren't used for grid storage, but today they're not. To point out a key area where chemists can do a lot of work is safe and stable electrolytes. In their solid state give the required power densities. You have all sorts of interfacial issues. And I think the proof there is in this Mercedes bus. This bus will operate all day long without needing to be recharged. It is using polyethylene oxide, electrolyte, lithium metal anode, and lithium iron phosphate cathode. It's being, batteries are being built by Blue Solutions in France. The company believes they can make these materials work at room temperature, but right now these batteries operate at 70 degrees centigrade. Key areas where chemists can play a role: we need new manufacturing technology to make the lead oxides, to make the lithium iron phosphates. All the way from the mine to the finished battery, we need to do better. Right now it takes 60 to 80 kilowatt hours of energy to produce 1 kilowatt hour of lithium ion battery. And Europe's taken the first positive step in that direction by having regional supply chains in the European program. So I think the ores are going to be mined in Scandinavia using low energy, clean hydropower, and then the batteries made in, say, Germany, Italy, or France. What we also need is new chemistry that can help pull apart the batteries after they've been used, so we can recycle everything in them and not toss them out. And the other issue we have to address are the side reactions, what causes the batteries to fade, and also so we can use all the materials within the batteries. In my last minute, 3 quick messages for the junior scientists, the students in the audience. You may be at a chemical society meeting, but remember, science is interdisciplinary. There are really no boundaries. The most exciting science is at the boundaries between the disciplines. And I use the examples, the 3 of us Nobel laureates. I'm a chemist, John Goodenough's a physicist, and Akira Yoshino is an engineer. Other key thing to remember, science is international. It knows no boundaries, even though the politicians may try to put them there. So I'm born in England. I made my inventions in the United States. John Goodenough was in fact born in Germany of American parents, but made his inventions in Britain, and Akira Yoshino made his inventions in Japan. And I think you all know we cross boundaries. This meeting of yours today and the rest of the week has speakers from around the world and attendees from around the world. Key point I want to make, energy storage is going to enable renewable energy. Huge push on now. It's going to be a huge push on new research to mitigate global warming, and I prefer to call it global messing up. We have issues at both extremes. And 2 little things on the right-hand side here. Facts do matter. In the US, I think we've turned things around now, but the politicians need to listen to our recommendation, not necessarily act on them, but they need to at least listen. And we all need to understand the cultures of others, because science is international. Americans don't think the same way or act the same way as Europeans, and certainly we all act differently to the Asians. We have to be able to understand that. So thank you very much, and I'll try to answer any questions you might have.
So thank you very much, Professor Whittingham, for your wonderful lecture, which not only looks at the past, at the history of lithium-ion batteries, but but also gives so many good hints for future research in the field, in which many different types of chemists might be involved fruitfully, and which might bring us to solve some of the big problems in energetics we presently have. Thank you again for having joined us today. And you have so many friends in Italy, especially in our electrochemistry division. And all of us are really looking forward to meet you in person next year, when you might come to visit us and continue lecturing us in such a wonderful way. Thank you very much.